I know we don't have a microphone, so if anybody up the back can't hear me at some point, put your hand up and I'll try and project. So this comes out of a project, a collaborative working group that we have been looking at trying to define extreme environments globally and in particular in North America, and look at how that has an influence on diversification and the species assemblage in global and in North America. So extreme environments sort of covers a grab bag of different habitats. So it can range from sort of locally, as you might have seen walking around, dry, arid, high UV, sort of your desiccated environments. At the other end of the scale, you can have your supersaturated, your waterlogged, high water environments, where maybe you have problems getting access to oxygen to the roots, or you have to deal with pathogens or waterlogging. You also have sort of cold environments where plants battle stress in terms of cell cohesion and other things associated with freezing and thawing and cold tolerance. You can have some soil factors, so cracking clays, which makes it very difficult for plants to sort of maintain a stable rhizosphere. Or maybe something like a serpentine barrier, where you have chemicals in the soil that make it very difficult for plants to tolerate. So you have a whole different range of environments that can be considered extreme. So this makes it a challenge to try and define extremes generally. There are a series of other problems when you're trying to define sort of extremes across a whole range of variables. One is that if you're asking biological questions, a lot of the habitats that are extreme are defined in the first place because they don't have very many plants. So if you're asking questions about diversity, you can start to fall into circular arguments about, does this area have few plants? It does because we defined it because it has few plants. Another problem is that what is to one organism extreme may very not be extreme to another organism. You get extremophiles that positively like these environments. Tend to be fewer of those, but it makes trying to define any one environment as extreme slightly problematic. Also, multiple factors can be extreme. So as we saw for your arid environments, you can have dryness is part of that, what makes that habitat inhospitable. You can also have high UV, you could also have soil drainage and other variables, all that contribute towards making sort of one of these environments a bad place to live. And so as a result, if you look through the literature, you often find that the thresholds for what are considered extreme vary from organism to organism, from study to study. And so, trying to tackle this problem, we had to try and come up with a way to sort of define extremes objectively. So, if we could do that, we could then start to test hypotheses of biological processes non-circularly. And so these things could be like whether particular traits are present in extreme environments or not, whether body size, if you're looking at animals, might change as you move into more extreme environments or not, and whether species diversity changes or is different between high extremes and low extremes. So, for terrestrial organisms, we can say that sort of ground level or thereabouts, the comfortable envelope of survival is round about the middle of the range of most variables. And this is sort of by definition, extreme being the ends of the variable. The ends of the variable are the variable space within which organisms are finding it difficult to survive. And so we just took a very straightforward a priori decision that we would classify the bottom 5% and above the top, the 95%, as being extreme for all the variables that we were going to consider. So we understand that that is an a priori and is not necessarily based on anything particularly biological, but that gives us this a priori flat standard that we can look at for all our variables. So we took climate variables from World Grid, which is 19 variables, and soil and elevation variables from the Soil Grid's 1 kilometre data set. This gave us an initial set of 40 variables, which we reduced down to 24 by looking at those that were correlated, removing those, and those that were relevant to organisms. Some of those variables are not necessarily going to be relevant to organisms we're looking at. So we then assigned each of those variables into 9 stress classes. So we looked and we saw that we could sort of determine the cold stress, so we're looking at those alpine areas or tundra areas, energy limitation, which is UV radiation, and UV temperature, Extreme variability, which is how much variance you have in a variable. So you can have something that goes from being very, very cold to very, very hot, something that's difficult for plants and other organisms to tolerate. Heat stress, fairly self-explanatory. High moisture stress, nutrient limitation, soil physical stress, UV stress, and water limitation. So just as an example, you can see for heat stress, the top above 95% for heat stress, we selected the variables of annual mean temperature, maximum temperature of the warmest month, temperature, annual range, and annual mean radiation. So we consider those variables all to contribute to the class of heat stress, and we assign these different variables to different classes. Okay. So in order to calculate our tail ends, our extreme ends of the variables, we divided the globe up into their continents. So this was we are working under the assumption that the organisms on each continent have maybe adapted to their local environments, and so by defining our variables in a sort of a regional scale, we might be sort of playing more towards the local organisms' tolerances. These also fall broadly into sort of ecoregions. So we feel that the continents as discrete entities do make some sort of sense. It also then allows us to compare our analyses across continents independently later on. So this was done at a resolution of 1 kilometre. Okay, so we did that for each of the different variables, and then we stacked these variables up by by the different variables in each class. So for high water stress, we've got topographic wetness, annual precipitation, precipitation of the wettest month, and mean annual humidity. So those variables all make up the class of high water stress. And so if we stack those on top of each other for each of the different classes, so again, these high moisture extremes, we get a heat map here that shows us where this class is more or less strong. So how extreme, the amount of extremeness in this class. So we can see that we have some but sort of low extremeness here. Only one of those variables that we put in the class is present in Greenland up here. But if we look at Central America, we see that all 4 of those variables that we have put assigned to that class are present in the same place. So we have a high level of extremeness there. We have all 4 variables acting at the same time in the same place. Okay, so we could use that. What we can also do is then we can take that layer and make it a binary, so we can say it's either extreme in a location or not extreme in a location. And then we can stack those for the 9 different classes on top of each other. And we can ask how many of the extreme classes, how many of the extreme layers are present in one location or not. So you can see here, we have high extremeness in southwest Western Australia. This was back to, this is the stacking of the 9 layers. We have high extremeness here in western US and into Mexico. We have also high extremeness here in the Andes. We get up to our maximum number of different variables right up here in the very high mountain peaks of the Andes. We have high extremeness in the Sahara region, the Middle East, the Tibetan Plateau, and Eastern Australia. So we can see that kind of fits with the areas in the world that we think might be extreme. But now we have a way of actually quantifying how extreme these different regions are. Okay, so sorry, just to blow that up so you can see. Okay, so now we have the original, the individual classes, so we can ask questions about whether, say, species diversity changes as you get more and more wet extreme or more and more heat extreme. But we can also ask whether you get more species diversity as all those extremes increase together. So in order to do that, we decided to tackle the second of those questions, whether as you add extreme classes, you get more or less species diversity. We took the species diversity map of Ellis et al. 2012. This consists of 16,500 equal area polygons for the entire globe, with a value for flowering plant richness for each of those. So we took the value of flowering plant richness from the centre of each of those polygons. We then matched that with the number of extreme classes that we also found at that same centroid. So now we have a value of the number of plant species in the middle of the centroid, and also how extreme the environment is at that same locality. Then we calculated the average species richness for each number of overlapping classes. So we took all the polygons where there was only one extreme variable and calculated the average species richness. Where there were two extreme variables, average species richness. So we have a response. We have how many classes, 1, 2, 3, 4, up to 14, and what the average diversity is for each of those numbers. Then we generated a null distribution by holding the number of classes constant and randomizing the diversity 99 times against that, and then calculating the averages for each of those. So what we get is something like this. So this is for the global. We see this is our actual diversity. So as we go through the number of extreme classes in a locality, so from no extreme classes present all the way up to 8, we can see that this is our reserve richness. It has a peak of 1 and then falls off through to 5 and 6, and then has a slight peak at 7 and 8. The blue lines here are our null distribution, so that's what we would expect if our data was randomized. So where the line is green, that shows that we are above or below our null distribution by 0.025. It's a two-tailed test. Whereas red, we suggest that our data isn't any more different than random. So we can see here that there is a general trend globally of a slight kick, but then as you get more extreme, as the number of extreme classes in the environment increases, we have a falling off of species diversity. And this is sort of as we would expect. As an environment becomes less hospitable, the number of plants that are able to survive there starts to drop off. Okay. Just as an aside, if anybody was wondering whether the latitudinal species gradient might have been playing into this, so is it just that we find more extremes towards the equator, and so we're just seeing the species gradient and these extremes co-occurring, and so that's what's explaining these differences. We did a regression of the number of extreme classes against latitude, and we found no particular significant trend. So if we plot that data, it does dampen the signal a little bit, but when accounting for the species latitude gradient, we still find that as you increase the extremeness of an environment, species diversity does fall away. If we look at each continent individually, so we just split that data up into the continents, we see that this same trend is played out in most of them. Africa, species diversity drops off as you get a more extreme environment. Also Eurasia. Australia, interestingly, sort of sticks around random. It doesn't look as though there's a whole lot of signal there. Diversity seems to be pretty much randomly distributed. South America has a very strong signal of decreased richness with extremeness. But North America shows a completely opposite pattern. So as you get more extreme, we start off below random, but as you get more and more extreme in the environment, the number of your species diversity actually increases. And this was a very interesting result. We were slightly puzzled as to why this might be the case. But we decided to test it with the one plant group that we're focusing on in the rest of our work. And this is the North American Botany. And this is a group that's incredibly diverse, 1 in 10 flowering plants in North America, and they're really well known for actually occupying some of these harsher environments. So you'll find them in the deserts around here, you'll find them in serpentine moles. So our expectation was that if we look at these in isolation, they might actually buck the trend in North America. We might find that there are more of these species growing in these harsh environments. So we aggregated a data set from GBFID Bio and Bison, which was for 3,100 species and about 500,000 records for composite day of North America. Using the 3 databases allowed us to cross-reference. Databases sometimes have different taxonomies, different treatment of the data, so we can use that to cross-check our data. We aggregated our species occurrences to 100 by 100 kilometre grid cells and calculated the richness for each. And we can see here, if we then plot species richness and extremeness, we have strong extremeness and richness in the southwest of the continent and Mexico. And if we plot that in a similar way to how we're plotting the global data, we see again, like North America, but against the global trend, as the extremeness increases, the number of compositae that are present there also actually increases. So it seems like they're actually attracted to extreme environments. To compare that to the North American, we see that it is a similar pattern. Interestingly, if you then subtract the compositae data from the rest of the flowering plants in North America, we find that the North American signal actually drops away almost entirely. So it looks as though the North American compositae are driving the signal of diversity in North America. So As a conclusion, we're trying to present a set of geospatial layers to represent these extreme classes. And if we test them, we find that, except in North America, species richness decreases as extremeness increases. And this can almost be completely explained by the composite A in North America. Just thanks to my working group, it's been a long trip. Also thanks to Jen Mandel for sponsoring me for another year of this work. Any questions on how much time we have?